So this is the last lecture. It's going to be about capacity expansion, which is the process that utilities go through in order to gradually increase the capacity of their generating resources in order to either meet electricity demand growth or more commonly to replace existing generation that comes offline and retires because it's either too old or it's retiring in order to meet more stringent environmental regulations. So this figure lays out the general scope of this challenge. We have demand that's increasing over time, although certainly demand is increasing faster in certain parts of the country and certain parts of the world than others. In the United States, demand growth is generally pretty low, especially if you compare it to rapidly developing countries elsewhere in the world. And in the United States, there are parts of the country that are experiencing loss of electricity demand while others are growing. In North Carolina, I think we're at maybe 1% or slightly less, although that is in some cases sort of a point of contention between the regulatory bodies that oversee the operation of Duke Energy and Duke Energy itself. But the job of Duke Energy here is to sort of hit a moving target, and that moving target is demand, which we've talked about is driven by demographic shifts, changes in technology, weather and climate on a year-to-year basis, and some other important drivers as well. The challenge is that our ability to meet that demand is sort of tied to adding, rather big power plants, right? We're not incrementally increasing our generation capacity 1 megawatt at a time. Our solution is sort of clunky because we're adding sometimes 100, 500, 1,000 megawatts at a time in order to meet growing demand, or in some cases to replace capacity that's coming offline because it's too old. And so you can see here that the clunkiness of our reaction to growing demand ends up creating occasional periods, mostly periods of under or over investment. And really what we want to do is try to follow this line of increasing demand, if it's increasing, and really minimize the severity of times when we have too much or too little capacity, because both situations are pretty bad. So we will have to figure out when and how much to build, and a big part of that is tying generation capacity expansion to forecasts of demand. And we've talked a lot about how peak annual forecasts are made. It's generally some sort of regression equation where we're predicting future demand, not throughout the year. We're really concentrating on the highest demand part of the year because that's the threshold for system reliability. As long as we have enough capacity to meet electricity demand in the highest demand hour of the year, then we're going to be okay the rest of the year. And so peak demand forecasting includes demographic data, economic growth, changes in consumer behavior, so efficiency, right, household efficiency in terms of energy consumption, and a lot of that ties down to what appliances people are buying and stuff like that. There are circumstances in which we experience surprises, right, where we make decisions based on forecast demand out into the future. And part of the challenge here is if you're talking about adding capacity, the consequences of doing that last a really long time. If you make a decision to build a lot more capacity based on this expectation, the demand is going to increase pretty consistently over the next 15 years, and you're wrong about that, then you're not just wrong next year, you're wrong for 15 years in a row potentially, and that can be really bad. Same goes if you sort of chronically underinvest in capacity. Then every year you're susceptible to critical shortages. And so it's, I think part of what makes this a really difficult exercise for utilities, probably the most difficult part of their job, is having to predict things way out into the future, because that's how long this infrastructure lasts. When you make a decision about building a power plant, you are making a decision that you're going to deal with for potentially decades. And I think just looking back at the history of the electric power industry, there has rarely been a period in which we can make sort of broad sweeping assumptions about what the next 20 or 30 years are going to look like and be right. And I would argue that that's even more the case now because of regulatory uncertainty and technological innovation. There's just a tremendous amount of uncertainty about what the future is going to look like. And I think a lot of that bodes well for proponents of the environment and climate change, because a lot of the shifts that are taking place are encouraging in that regard. But if you're a utility, it's really, really scary, and it's really, really hard to make a good decision. So an example of the consequences of chronic underinvestment in capacity is the California electricity crisis. And we've talked about this sort of in passing one time before, about how weather and climate can impact electric power systems, and how shocks and failures can be modeled in power systems, and how they can translate from the physical infrastructure side to actual real financial and economic consequences. And so this was sort of a perfect storm of events that resulted in the California electricity crisis. You had some aspect of this being caused by incomplete market deregulation. You had significant drought in the Pacific Northwest, which reduced imported hydropower into California, and high natural gas prices, sort of as a result of both, but also because of market manipulation. And you had gradually increasing electricity demand and not enough of a financial incentive on the part of utilities to meet that via increased capacity. And so you were sort of setting up California to experience a failure because utilities were underinvesting in capacity for many, many years. So that's one example of underinvestment in capacity and how that can cause problems, and it did cause significant problems. One giant electric power utility went bankrupt. Another one should have, but was bailed out by the state government, and taxpayers in California have been sort of paying for that ever since. There's an equally sort of consequential circumstance that is tied to overinvestment in capacity. And this is sort of related, actually, to the California electricity crisis. Overinvestment in capacity in the 70s is sort of one of the main drivers behind deregulation of the electric power industry, which I mentioned is part of what caused the California electricity crisis. So what happened in the 70s is that you had a really rapid demand growth for electricity following World War II. In order to build that, and that sort of coincided with our development of nuclear power capacity in the United States. And so to meet this growing electricity demand, utilities built a lot of nuclear power capacity. But what factored into that decision was this expectation that electricity demand was going to continue to grow almost exponentially. And what ended up happening is that demand did increase, but it increased linearly. And so we had much more capacity than we actually needed. And paradoxically, like if that happens, if you build too much capacity into a system, electricity prices go up, right? And so it's a little bit different than a market-based situation where, if supply goes up, prices tend to go down, and if supply is scarce, prices tend to go up. These are monopolies, right? And so they are spreading their fixed costs over their entire customer base on a dollar per megawatt hour basis. And if those dollars stay the same, and a big part of the dollars are the fixed cost, the infrastructure cost of building power system, and the megawatt hours declines because they're selling electricity, the amount of money they have to charge per unit of electricity they sell increases. And so in this is a case where we've talked a lot about this trade-off between redundancy and cost, where you can always improve reliability and increase system redundancy, but at a certain point it costs you more and more to do that. And so this is sort of a similar example where you had basically just too much capacity, too much redundancy built into the system, and retail electricity prices increased. So here's just an illustration of that. You had, in the United States, residential electricity prices declining, basically since the inception of the electric power industry. And, you know, this is hard to overstate the importance of declining the cost of electricity in the economic development of the United States. And so you get to the 70s, and then this particular situation plays out. So the solid line here is what electric utilities in the United States thought electricity demand was going to do. That was based on their prediction. And the dotted line that's much lower, the linear line, is actually representative of what demand actually came to pass, right? So demand certainly did increase, but at a linear rate. And so the difference between those is sort of the demand shortfall that was part of what resulted in retail electricity prices increasing. And just sort of a note that's interesting, this bias, I think, among utilities to predict increasing demand over time and to overpredict demand increases over time is not limited to the electric power industry. It's very, very common for water utilities to do the exact same thing. And I think there is a sense that they're, among decision makers, that they're sort of being prudent. And in the electric power industry, it's a little complicated because there's an actual incentive for utilities to build more because they're publicly traded companies. But in the case of water utilities and electric power utilities, I think there is this sense that building more redundancy into the system is a way to minimize risk of failure. And that is true, right? But as we've talked about several times, lowering that risk of failure does come at a cost, and it might not be the most efficient way of doing things. And so, as a result of overbuilding capacity, overinvestment here, electricity prices actually go up here. It's because demand is not high enough to justify the really substantial capital costs that were required and needed to be paid off over time as a result of building a lot of nuclear capacity. And there were other sort of extenuating circumstances here, including multiple oil crises that caused electricity prices to increase as well. But a big part of this was overinvestment in capacity. And this overinvestment was really viewed as this source of ineptitude and the inability of regulated monopolies to make efficient decisions. And this was what precipitated, in many cases, this movement towards wholesale electricity markets and market deregulation, which is what we mostly have in the United States today. So those are the pitfalls of overbuilding and underbuilding, and you really want to hit the nail on the head, and that's very difficult to do, as I mentioned, because you're not using a little hammer to hit the nail, right? You're using something much bigger, something much clumsier. You're making capacity additions many hundreds of megawatts at a time, whereas demand typically doesn't increase or decrease on that scale. And so it's sort of a perilous process to begin with, but there are specific sources of uncertainty that really create a lot of the risk for utilities. And the first is demand, and we've talked about that. We really want to try to minimize the periods of over and under investment when you're adding capacity, right? And we've seen that it can be disadvantageous to have both under and over investment, and they cause sort of different problems. One is, if you overinvest, then you just have higher electricity prices than you should. If you underinvest, you can set yourself up for actual physical failure of the grid. There are a number of other sources of uncertainty, though, in capacity expansion planning that have to be considered, and the first is market-based uncertainty. And a lot of these sources of uncertainty can sort of go hand in hand. Certainly fluctuations in fuel prices, especially natural gas prices. Coal prices are relatively stable, but at least historically, not recently, but at least historically, natural gas prices have been a tremendous source of uncertainty. And that uncertainty itself, I think, causes utilities to shy away from going all in on natural gas. Even in a world that we are in now, where natural gas prices have been pretty consistently low for 5 or 6 years. A lot of the people that work at utilities lived through the 90s and the 2000s. And they are, they remember times when, natural gas prices would, double with very little warning. And they would double because of a hurricane, or they would double because of market manipulation, or things that were sort of outside of their control. And that source of uncertainty just itself, even if gas prices stay low, I think this institutional memory of uncertainty can dissuade utilities from making certain types of decisions. But certainly, I do think having really low natural gas prices probably even more than renewable energy has had a transformative impact on the electric power industry. I mean, it's precipitated, in conjunction with, obviously greater regulation on coal plants, this widespread retirement of coal-fired power plants in the United States. And natural gas prices aren't just bad for coal. It's really bad for nuclear because it depresses wholesale electricity prices, and it's pretty bad for renewables too. Renewables rely on having a high price, as high up as possible, a price of electricity in order to recoup capital costs. And so, natural gas prices have been good in a lot of areas, but they sort of destroy all other alternative sources of electricity. And so that's sort of something to keep in mind as well. So here's just an illustration of the difference between natural gas prices and coal prices. All these units are in dollars per million BTUs. So that's a way to compare coal and natural gas prices on the same dollar per unit fuel scale. And we've talked a lot about sort of this time series of natural gas prices and what specific events, are tied to each of these really big dramatic events. And it's sort of like a history. You can go through and see any really, really big change in natural gas prices. There was a really good reason for why that happened. Now, coal obviously is much more stable, and that's because we have a greater supply, greater ability to store fuel. A big part of why natural gas is more volatile is because storage capabilities for natural gas in the United States are much more limited. So sort of going hand in hand with markets as a source of uncertainty is technology, and certainly you could include horizontal hydraulic fracturing as a technological innovation that has changed markets. I think certainly when we think of technology and the ability to really disrupt the conventional utility model, right? Centralized production of electricity and, utilities that are monopolies, stuff like that. Certainly variable renewable energy and energy storage come to mind. And I think they are transforming the utility industry, and one of the main ways they're doing that is through capacity expansion planning. And that's because capacity expansion planning is a very forward-looking exercise. If you looked at, a pie graph of how much variable renewable energy is, contributing to the amount of electricity that we consume in the United States relative to coal, relative to natural gas, nuclear, it would be tiny. It would still be tiny, even at the high growth rate that it's experiencing now. But the one opportunity utilities have to sit down and really sort of look themselves in the mirror about what they want to invest in is capacity expansion planning, because it requires them to look 30 years out into the future. And now I think looking 30 years out into the future, no one would suspect that renewable energy is going to remain at 6% of national energy consumption. And I think the rule of thumb is not if, but when renewable energy sort of takes over everything and becomes the really dominant resource on the grid. Now, I think the when is very, very important here, because if you are a publicly traded company, or so you're beholden to shareholders and your investors, the people that loan you money. You're also sort of beholden to your ratepayers, right? And you have some obligation to minimize the cost of producing electricity, of meeting electricity demand. And so a really big source of uncertainty is the trajectory of cost of these renewable and energy storage technologies. If they go down more quickly than anyone expected, and that has sort of been the case over the last 10 years, that can not necessarily strand investments in the truest sense of the word. A lot of utilities may still have legal pathways to recoup those costs, but it could ultimately be a disadvantage for ratepayers, right? Imagine if Duke Energy decided today, or the Southern Company decided today, the cheapest way for us to produce low carbon electricity is to build some new nuclear power plants, right? And then those last 50 years, and then over the next 10 or 15 years, there are just continuing breakthroughs in solar and energy storage that allows us to meet baseload or to replace baseload sources of generation like coal or nuclear with a combination of solar and storage and demand response or whatever else, way cheaper, right? And so that would end up being a terrible mistake, or at least the decision in hindsight would look like a terrible mistake to build a nuclear power plant. So that's the risk of technology here. I mean, from our standpoint, it's super exciting, but if you're somebody that has to make a long-term investment about how you're going to provide electricity, it's an increasingly very, very risky situation, and part of that risk comes from the rate of technological innovation. So one of the more interesting sort of phenomenons about the development of variable renewable energy, in particular solar, but also now if we sort of include battery storage in that family of technologies as well, is the sort of collective underestimation of the rate of cost reductions. And that has been, that goes all the way sort of to the top in terms of the U.S. government's ability to track changes in the cost of different technologies as well, and their attempts at predicting those continued changes out into the future. So far, I mean, if we're talking about solar and energy storage, most predictions about where we're going to be into the future look very conservative, and what that means is the cost is coming down much quicker than anybody sort of anticipated, and that's awesome. But again, that's a big red flag if you're a utility that's conceivably gonna go a different direction, right? If you decide to invest, particularly in a really, really long-term investment like nuclear, building a natural gas plant over the next 5 years or so maybe not such a bad idea because the lifetime is only 20 years or so, the depreciated lifetime. So then you can sort of join the solar and energy storage bandwagon at that point, if that's a viable choice. But if you build a nuclear power plant, you are stuck with it for 50 or 60 years in some cases, and so that's a big risk. Building such a long-term decision into your rate base and your cost structure, given the rate at which these other technologies are declining in cost. So markets and technology, I think people are sort of used to predicting. We're wrong a lot, but we know we're wrong a lot, and we have ways of quantifying how wrong we're going to be and exploring the sensitivity of our assumptions to the decisions we make. Regulatory uncertainty, and I think we are all acutely aware of how policy can be sort of implemented and then whisked away over a very short period of time, is the hardest one to describe here in any sort of statistical manner. I mean, if you think back to our discussion of decision analysis and stochastic optimization, that's where we're headed with this discussion of capacity expansion. And so our ability to quantify what an optimal decision here is really based on our ability to describe uncertainty in a probabilistic way. And I think it's very, very difficult to think about what the likelihood is of the United States enacting a carbon tax, or strengthening the Clean Power Plan, or removing the Clean Power Plan, or anything else like that. And I think that is one of the most harmful. Regulatory uncertainty, just the uncertainty, is one of the most harmful aspects to power system planning in the U.S. It goes, I think, well beyond the challenges posed by markets and technology. And I think that's something that any utility executive would tell you, and it's really hard to incorporate into decision making. And so I think whether or not we have something that looks like a carbon tax or not, I think the perception among utilities is that that's where we're headed, and I think that's an interesting sort of an interesting phenomenon, because you have these utilities that are very conservative, at least in terms of how they make decisions, right? They're relatively risk averse. And just the threat of regulations, I mean, there doesn't have to be an actual strong possibility for a carbon tax to be enacted. If the utilities just sort of get a whiff of that, then they often will turn to just implicitly charging themselves for carbon. And that has been the course of action that many utilities in the United States, including Duke Energy, have taken when they undergo capacity expansion planning exercises. They almost always assume a carbon tax in the future. Now, the size of that tax can vary, and that's a source of uncertainty. But if you're a utility, the threat of regulation here is almost as good as actually having a regulation. So other important considerations in capacity expansion planning is construction time. It takes a really long time to build power plants, some more than others. Obviously nuclear power plants take a really long time to permit, go through all the regulatory channels, and then build. Also retirements. I think that we're really moving away from true capacity expansion now in the United States. Most of the new construction in power plants that's going to occur, I think, over the next 20 or 5 years or so, is not going to be to meet increasing demand. It's going to be to replace existing capacity that's coming offline, either because it's too old or because it doesn't adhere to stricter environmental regulations, whether that's carbon emissions or something else, water consumption, other air emissions like mercury and air toxics. So really, I mean, if you talk to Duke Energy, folks there, the way they think about capacity expansion is really retirement management, right? They have all these coal-fired power plants that they would love to get rid of as fast as possible, for a variety of reasons. It's a liability in terms of carbon emissions, it's a liability in terms of coal ash, it's a liability in terms of water consumption, public perception. It's less flexible for dealing with increased renewable energy. They want to get rid of that stuff as fast as they possibly can, but they also want to make money, and so they're not going to retire these plants before they're ready financially to retire. So they're planning. The exercise for Duke Energy is basically what's going to replace all that coal. Is it going to be solar? Is it going to be natural gas? Is it going to be nuclear? Is it going to be some combination, something else? That's the question that they're really having to address. Even in a state like North Carolina, where demand is increasing, I think most of their capacity additions over the next several decades are going to be due to retirements. So let's look specifically at Duke's situation. This is information for the Duke Energy's, or the legacy Duke system, which is the western half of North Carolina, a really, really big part of South Carolina. So this is not what we would refer to as the Duke Energy Progress, right? So the system in the eastern half of North Carolina that was Progress Energy, that was bought by North Carolina, by Duke several years ago. So this table shows you roughly what they own right now in terms of capacity. So a lot of nuclear, a lot of coal, a reasonable amount of hydro, an increasing amount of gas. Most of that is, at this point, I can't remember if it's all combustion, or it's some mix between combustion turbines and combined cycle. And then there's a list of all the sort of general system characteristics over to the right. Their winter peak's about 16.5 megawatt hours, and then summer peak 17,000. Although that seems a little low, actually. I think their summer peak's a little higher at this point. So these numbers might be slightly fabricated. Peak load growth's about 1% per year. That's sort of a rule of thumb for a lot of places in the United States, although some are less, some are slightly more. They have to build in some system redundancy, right? And we've talked about how you do that and the metrics for doing that. We use this term, the reserve margin, which is a measure of how much capacity they have sort of left over after they're dealing with peak demand. And remember, we've sort of talked about the need to provide spinning and non-spinning reserves in electric power systems, and the rule of thumb for doing that is this N-1 criteria. So you have to provide enough reserves to meet the largest single contingency in your system, which is usually a nuclear power plant. So if there's a nuclear power plant that's 2,500 megawatts, Duke at all times has to have backup capacity available to meet a sudden increase in demand of 2,500 megawatts or a sudden decrease of supply of that same amount. So a lot of planned retirements here. So they're going to basically get rid of all their existing coal-fired power capacity over the next 30 years, I would say. So that's going to be a gradual process. Basically, looks like every 5 years they're going to retire something. And this is, don't quote me on this, I think I sort of pulled this in for the sake of developing this exercise, but this is pretty realistic. Like, they're trying to get on the coal off-ramp as quickly as possible. What they're constrained by is accounting and finance. So if you put all those numbers together, and you start with what we have in the Duke system today in terms of installed capacity and what peak electricity demand is, and you gradually increase summer peak load over the next 25 years or so, and at the same time you pull out capacity that's going to be retired, what you end up with is this black line, which is a measure of how much new capacity is needed, cumulative capacity is needed over time, what's going to be needed over the next 25 years. And what this suggests is that by 2040, Duke's going to need to come up with, another 7,500 megawatts or so of generation. And most of that's going to be to replace existing capacity, coal-fired capacity that's going to retire. So we have a number of options, or Duke does, for filling that void, which is, again, mostly going to be created by retiring a bunch of coal-fired power plants. So this table lists out the options that they're mostly considering at this point for meeting capacity additions, not out to 2040, but the next round of things that they're going to build, they're going to be choosing from this list. So that's nuclear, coal with carbon capture and storage, natural gas combined cycle, solar, wind, efficiency, and then combined storage and variable renewable energy. So battery and solar, or battery and wind. And we're going to assess these options mostly from the standpoint of cost. And we're going to consider some aspect of their ability to help meet system reliability as well. So the capacity value here is a measure of how much capacity that we add. So if we add 2,000 megawatts of a nuclear power plant, how much of that capacity can we actually consider going towards meeting our goal of 7,500 megawatts that we need to add in order to meet peak electricity demand in 2040. And so you can see that all of the capacity values are 1 except for solar and wind, except for variable renewable energy. And what that means is that when we're thinking about adding solar and wind, we have to discount them because having 1 megawatt of solar doesn't help you meet peak electricity demand during the year, the highest peak electricity demand during the year, the same way a natural gas combined cycle would, which you can turn on and control. Same thing with wind here. And so there's a lot of truth to the fact that, especially in summer, the availability of solar does overlap more closely with peak electricity demand patterns than, for example, wind is pretty close. But it's not perfect, and so we're going to err on the side of caution here and say that we're gonna discount solar and wind more strongly and equitably here, which is probably also not true. And the other thing to consider here is that I don't actually think Duke is considering building any wind. They're mostly considering building solar, but any other utility in the United States, or many other utilities, would be considering wind alongside solar. So that's the only consideration we have here towards the ability of these resources to actually help ensure system reliability. In reality, this whole process, this capacity expansion process, would include some exercise in using unit commitment models to assess system behavior over a wide range of different circumstances to make sure that the portfolio that they actually put together that's theoretically going to be available in the future is sort of robust and reliable. So again, the main metric here we're dealing with is cost. So the levelized cost of electricity for each technology listed here, which is $1 per megawatt hour amount that equates to the amount that they would have to charge per unit of electricity to recoup all costs, not just operational costs, but also capital costs associated with building these power plants. And so what that means is that you build a nuclear power plant, and every unit of electricity that comes out of it, you charge $102, for every megawatt hour. Then over the entire lifetime of that power plant, discounted, you will arrive basically at a break-even point, and that would include being able to repay all the people that provided you capital, whether that's equity investors or lenders. And so clearly there's a big range of cost here. The most expensive option is battery and solar and battery and wind. And most of that, of course, is going to be due to the battery, because solar and wind by themselves are among the cheapest sources of electricity. Nuclear is more expensive than natural gas. So's obviously coal with combined cycle, or coal with carbon capture and storage. The cheapest option available is natural gas, and then wind. Depending on where you are in the United States, wind is actually cheaper than natural gas. If you're building a wind turbine where the wind speeds are higher, then the levelized cost of electricity from wind goes down quite a bit. And then we also have some different constraints on the minimum amount we can build. So we're not going to be building a nuclear power plant 5 megawatts at a time. That's part of the issue with nuclear, is that if you go all the way. You have to build a very, very large power plant. That's part of how nuclear power plants arrive at a point of economic competitiveness, is that they're very large, right? So they can spread those fixed costs out over many units of electricity sold and achieve economies of scale. Same goes with coal. You're not going to be building, I don't think, anything less than 1,000 megawatts of a coal-fired power plant. We're not considering building coal without carbon capture and storage, so I think that's owing to regulatory concerns mostly. We've basically ensured that no one's going to build a new conventional coal plant in the U.S. ever again. Combined cycle natural gas plants, again, that still you have to build pretty sizable plants. The greatest flexibility we have in meeting very incremental, smaller changes in electricity demand or losses of supply is variable renewable energy. You can build about 5 megawatts at a time, combine them with batteries and to achieve some sort of baseload resource. I don't have listed here a minimum in terms of efficiency, but there is a maximum listed there. And so what that suggests is that we can only go so far in becoming more energy efficient. There's going to be a point at which becoming more energy efficient is not cost effective. And so at the $25 per megawatt hour basis here, we can only really extract 200 megawatts from efficiency. So we can look at, this is the orange bars here equate to that black solid line that I showed a few slides ago, which is the cumulative amount of new capacity needed over time. And we end up in 2040 with Duke needing about 7,500 megawatts of new capacity. Again, most of that's going to be replacing units that are retiring. The blue bars show you what the incremental changes are, and so this gives you a sense for how they would actually attribute year-to-year changes in the need for capacity to decisions about specific projects. So how do we go about making this decision? Obviously, we want to minimize the cost while also meeting some sort of constraint about reliability. And in this case, because we are incorporating sort of a discounted capacity value for variable renewable energy, and our constraint here is to meet our long-term demand predictions and our incremental demand predictions, then the main constraint on the system is that the cumulative amount of capacity we add not only gets us to about 7,500 in year 2040, but along the way meets our incremental changes in electricity or need for capacity that's caused by periodically us Duke retiring a coal-fired power plant. So we can set it up as a mixed integer linear program here. So we're trying to minimize the cost of meeting our capacity targets, and so we have for each choice about what technology we use here, we have represented the levelized cost, the capacity per plant, and then a binary variable. So the x's are all binary variables. X1 would be the number of nuclear power plants completed in period T, and then X2 would be the number of coal plus carbon capture and storage, etc. And so we're representing here the levelized cost of electricity, the capacity per plant that's added, and then the number of plants that are added. And so the sum of all of this, is the objective function that we're trying to minimize, but the sum of all of this has to also meet our constraints. So if the incremental need for capacity in period t equals 2 is 1500, then all of the x's in period 2 have to be, or the x's times the capacity per plant has to be greater than 1500, etc. So again, the constraint here is incremental. So we're going to subject the solution of this objective function on a period-to-period basis, where each t is this 5-year increment over which we know we're going to experience changes in a need for capacity. And so for every period t, we have to meet the incremental demand change. And we are also going to implement in this constraint the fact that adding renewable energy doesn't help us meet that demand change as much as, for example, adding a natural gas combined cycle power plant. So we're discounting the capacity value of both wind and solar here by multiplying each of their capacities and the binary variables associated with each times 0.4. And so if we solve something like this, what we would end up with is the fact that Duke's going to take advantage of efficiency more or less first, because they want to. That's sort of the low-hanging fruit, right? If it truly has the lowest levelized cost of electricity, then we'll exhaust that first, and basically add 200 megawatts of efficiency every incremental period. So we're exhausting efficiency, and we use a combination of natural gas and wind after that. So that represented the solution if we really trust the values that we put on the levelized cost of electricity. In particular, if we assume that those numbers are going to remain the same over our planning period over the next 25 years. And of course, that's not true at all. So one of the things we want to do is investigate how long-term changes in the cost of variable renewable energy, battery costs, policies that might impact the cost of carbon emissions, in particular from natural gas combined cycles units. We want to understand how those sources of uncertainty would impact the choices we make. Again, sort of assuming that we're 100% sure things are going to look like this. So we're not looking at an ensemble forecast yet. We're just assuming that let's look at a world in which in 2025 a carbon tax is enacted that because it's charging a certain number of dollars per ton of carbon emitted, it increases the levelized cost of electricity of natural gas combined cycle plants to $100 in 2025, and that increases up to 2040 because of increasing natural gas prices. And then let's look at the impacts of gradually decreasing cost of variable renewable energy, and I have noted here Swanson law. So just this fact that variable renewable, in particular solar, is declining in cost because of, for a variety of reasons, advances in material science, but also the experience curve, economies of scale, etc. So let's say solar declines to 45 dollars per megawatt hour, and so does wind, eventually up in 2040. Efficiency stays the same, and then let's say battery costs also decline substantially because of Elon Musk or some competitor of his, or somebody that we don't know about yet. So the way, of course, that would be implemented in the optimization program is that the costs in our objective function and in our objective function would change over time, right? So in period t equals 1, our costs would look different than in period t equals 5. And as a result of that, we experience a different outlook about what's going to be used. We're still using a lot of efficiency, so the rule of thumb here is implement efficiency if you can. If it ends up being actually the true low cost resource, wind is added up to a certain point. Still using a lot of natural gas, but the main effect of having a carbon tax in place is that after 2025, Duke ends up adding a lot of nuclear power. Because it's it's still assuming that solar and wind with batteries are going to be too expensive, that it's not going to be cost competitive with either natural gas or nuclear. And if there's a carbon tax in place, then natural gas loses market share to nuclear. And this is eerily similar to what Duke has actually publicly said it's going to do. If we look over the next 15 years, they're looking at adding energy efficiency, renewables, demand-side management, natural gas, and nuclear. I think the results of the optimization here was a little light on variable renewable energy, and I think part of that's because it doesn't reflect the particular circumstances that Duke experiences in North Carolina, where it's basically legally obligated to buy variable renewable energy from utility scale developers if it's offered. And so I think this is what Duke is expecting to build over the next 15 years, and that looks pretty good. I mean, this would substantially, presumably this is all going to be replacing coal-fired power plants. And so if we replace coal-fired power plants with a combination of renewables, nuclear, and natural gas, that will substantially reduce carbon emissions from the electric power sector, especially if we keep doing that over the next 25 years. It will not drop it to zero, and that's basically what needs to happen from the electric power sector if we're going to do something substantial about climate change. So in that respect, it's kind of disappointing that we're sort of stuck with natural gas. And I think in many circles, the decision to rely on nuclear way out into the future is viewed as extremely problematic as well, for a variety of reasons, some of which I mentioned here already. You're sort of stuck with nuclear if you build it for 50 years, and so if you do that, then you're sort of locked in, and you don't get to potentially alter that decision to reflect changes in the market or technology or water availability, etc. So a lot of people view this nuclear option as a little iffy. I'm probably in that camp, but if it's the best available resource to lowering carbon emissions, then it's worth considering. So one thing to keep in mind is that when we set this mixed energy optimization program up to minimize the cost of meeting incremental changes in demand for new capacity, even if we are assuming that the levelized cost of electricity for these different technologies is time varying, we're eliminating all uncertainty here. So we're just assuming that there's one possible pathway things could take, and that's clearly not true. And so part of this process is going to be incorporating uncertainty about how things could evolve, and some of those sources of uncertainty could be how growth and demand for electricity is going to change over the next several decades, and whether that's going to be correlated with changes in technology like the availability of solar and batteries, and how fast that technological innovation occurs, and whether or not the electrification of the transportation fleet needs to be considered, and how widespread that becomes in terms of affecting the operations and sources of electricity consumption in the United States. So all of these possibilities are ones that a utility would have to include, at least nominally, in the consideration about what they're going to do over the next several decades. It might not impact what they do in the next 5 years, although you never know until you include it into the objective function of this optimization. So how would we explore these possibilities? So one option would be ensemble prediction, or at least, an ensemble, not necessarily prediction, but ensemble stochastic simulation, looking at a really high volume of possible pathways that all of these different sources of uncertainty could take, whether it's regulations, technology, markets, trying to understand how they're correlated, and looking at a lot of different potential future sort of states of the world. One of the issues with doing this, and again, I think this is sort of a part of what makes me feel a little empathetic towards electric power utilities, is that, when we were talking about, when we were doing like ensemble forecasting and stochastic simulation, and incorporating that into the objective function of optimization programs, we were sort of leaning on having historical data available that allowed us to quantify the uncertainty in some of these important drivers. And the truth is that a lot of the challenges facing the electric power industry are linked to irreducible uncertainty. In other words, we may have sort of like qualitative estimates about how things are going to occur, but if you're trying to come up with an expected value or make a decision where you're trading off expected value for standard deviation in some sort of performance metric, that ultimately relies on some assumption you're making about the statistical characteristics of the process you're modeling and the source of the uncertainty you're incorporating. And we may not be able to do that, not just for regulations, but also technology as well. And so that sort of moves the discussion a little bit beyond the whole idea of sort of like risk-reward trade-offs. It's more about vulnerability and robustness. And in that case, it might be a better idea to first identify, in terms of assigning the likelihood of certain outcomes occurring, trying to understand which outcomes for which decisions we make are unacceptable, right? Like if we build a nuclear power plant, under what circumstances does that drive us out of business, right? And then that sort of gets us to the point where we can start thinking about decisions and linking them to outcomes that sort of are so severe they're unacceptable. And we can start thinking about culling certain decisions that have enough circumstances, whether they're likely or not, that would sort of eliminate our ability to be successful. And so that goes a little bit beyond optimality, right? So we're not necessarily maximizing or minimizing anything. We're really looking for situations in which we're setting thresholds for performance, and we're going for a decision that, results in outcomes that are within that threshold for the widest set of possible circumstance. And that's sort of moving towards robustness and away from the specific definition of optimality. And along with that, there is something that we talked a little bit about in terms of decision analysis, which is real option theory. And so if you are subject to sources of uncertainty that you cannot describe, right? There could be some value in just delaying big decisions, right? I think there's this sort of view that at some point the uncertainty about regulations will be resolved, right? And what's painful is actually having to make decisions before that gets resolved. And you could almost see the same argument being made for technology, right? There's sort of conceivably a limit to how cheap batteries and solar could get. Or we could view it a different way. We could say, based on how much capacity we know we're going to need over the next 25 years or so, what really matters is how quickly batteries and solar decline in cost over the next 10 years, right? Beyond that, maybe it won't affect our decision that much. We'll go for it anyway or not go for it. So there's a lot of value in terms of eliminating the possibility for things to go really badly, right? Making a decision like building a new nuclear power plant and then having to suffer the consequences of that decision. There's a lot of value, which we call real option value, in actually delaying big decisions or making a specific investments that keep your options open and keep you flexible in the future. And you can actually quantify the value of certain decisions like this. And this all builds into a type of decision analysis called real option theory. And so this is one of the main justifications that many people give, including Duke, for the value of utility scale solar, in particular in North Carolina, and just the idea of adding variable renewable energy. I think one of the things that is sort of frustrating to point to is the fact that the scalability of renewable energy, at least on a sort of like centralized production of energy basis, is less, right, than like just building one big nuclear power plant, right? We have to do it like 5 megawatts at a time. You don't have to, but in North Carolina it's sort of advantageous to do that. But there's an advantage to being able to just add 5 megawatts at a time, and that is that it allows you to potentially postpone, maybe not put off completely, but it allows you to postpone a really big decision. And there is enormous value in that, and part of the value of that comes from being able to resolve uncertainty about regulations, technology, markets. You just get to wait and see how those things evolve, and it doesn't mean that they're going to be less certain in the future, but it might. It might mean that some of those things that could cause big decisions you make to be disasters, some of those may become clear and would allow you to say in 5 years, reassess your decision to build a big nuclear power plant that could last decades. You might 10 years from now, for whatever reason, might clearly see from just an economic standpoint that that's a bad decision. And so that's one of the values of having this ability to add renewable energy a little bit at a time. And I think Duke does acknowledge this value. All right, that's it. This is the last slide of the last lecture. So, thanks for being a great class. And we will explore these concepts in more detail on Tuesday, and then we'll get ready to take the final. Thanks again, and I will talk to you on Tuesday.